Imagine a particle so small and elusive that it can pass through the entire Earth without interacting with a single atom. Now, imagine that trillions of these particles are zipping through your body every second. Welcome to the fascinating world of neutrinos, the universe's most ghostly particles. These subatomic wanderers have captivated scientists for decades, earning nicknames like ghost particles and cosmic messengers. Neutrinos are everywhere, yet they're almost impossible to detect. They're born in the fiery hearts of stars, in the violent deaths of massive stars, and even in nuclear reactions here on Earth. Despite their abundance, neutrinos remain one of the most mysterious particles in the cosmos. What makes neutrinos so fascinating is their potential to unlock some of the universe's deepest secrets. These tiny particles could hold the key to understanding why matter exists at all, how stars explode, and even what's happening in the most extreme corners of the cosmos. Let's break it down to the basics. Neutrinos are subatomic particles, which means they're smaller than atoms. They're part of the family of particles called leptons, which includes electrons. But unlike electrons, neutrinos have no electric charge and almost no mass. There are three flavors of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. Neutrinos can change from one flavor to another as they travel through space. This phenomenon is called neutrino oscillation, and it's one of the many puzzles that make neutrinos so intriguing. Neutrinos interact with other matter through the weak nuclear force, one of the four fundamental forces of nature. This means that neutrinos rarely interact with anything. Despite their ghostly nature, neutrinos are incredibly common. Neutrinos play a crucial role in the cosmos, acting as cosmic messengers that carry information from the farthest reaches of the universe. They're produced in some of the most energetic events in space, such as supernovas, the explosive deaths of massive stars. When a star goes supernova, it releases an enormous burst of neutrinos. In fact, about 99% of the energy from a supernova is carried away by neutrinos. These particles are also key players in the nuclear fusion reactions that power stars like our Sun. The Sun produces a staggering number of neutrinos every second as a byproduct of the fusion processes in its core. These solar neutrinos stream out into space, providing us with real-time information about what's happening in the Sun's heart. Neutrinos are also time capsules from the early universe. Because they interact so weakly with other matter, many of the neutrinos created in the first few seconds after the Big Bang are still zipping around the cosmos today. If we could observe this neutrino background, it would give us a snapshot of the universe when it was just seconds old. The elusiveness of neutrinos is both their most frustrating and most fascinating quality. But why are they so hard to detect? The answer lies in their fundamental properties. Neutrinos are neutral particles, meaning they have no electric charge. This is crucial because many particle detection methods rely on the electric interactions between particles. Moreover, neutrinos have an incredibly small mass. For a long time, scientists thought they might be massless, like photons or particles of light. We now know they do have mass, but it's so tiny that it's still not precisely measured. The combination of no electric charge and minimal mass means that neutrinos primarily interact through the weak nuclear force. This elusiveness makes neutrinos both a challenge and an opportunity for scientists. Their ability to pass through almost anything unimpeded allows neutrinos to carry information from places in the universe that we can't observe by any other means. Section 5. Catching the uncatchable. How scientists detect neutrinos. Given how elusive neutrinos are, you might wonder how scientists manage to detect them at all. The answer lies in some of the most impressive feats of engineering and patience in the scientific world. Neutrino detectors are typically massive structures designed to maximize the chance of a neutrino interaction occurring within them. One common type of neutrino detector uses large tanks of ultra-pure water. These detectors, like Super Kamiokande in Japan, are often built deep underground to shield them from cosmic rays and other interfering particles. When a neutrino interacts with an atom in the water, it can produce a charged particle that moves faster than the speed of light in water, creating a shock wave of light called Cherenkov radiation. Another detection method uses vast amounts of clear ice, like the Ice Cube Neutrino Observatory at the South Pole. This detector uses a cubic kilometer of Antarctic ice, instrumented with thousands of light sensors. When neutrinos interact with the ice, they produce particles that emit Cherenkov radiation, creating a trail of blue light that the sensors can detect. Section 6. Neutrinos in everyday life. Surprising analogies. While neutrinos might seem like esoteric particles confined to the realm of high-energy physics, we can draw some surprising analogies to help understand them better. Think of neutrinos as the ultimate introverts at a party. They're there, mingling among all the other particles, but they rarely interact. They pass through the crowd without bumping into anyone or striking up a conversation. Or consider neutrinos as cosmic ninjas. They're stealthy, nearly invisible, and can pass through solid objects without leaving a trace. Just as a skilled ninja can infiltrate a heavily guarded fortress undetected, neutrinos can zip through planets, stars, and even entire galaxies without anyone being the wiser. Another way to think about neutrinos is as nature's own fiber optic cables. Just as fiber optics can carry information over vast distances with minimal loss, neutrinos can bring us news from the farthest reaches of the cosmos. Section 7. The Neutrino Factory. Where do these particles come from? Neutrinos are cosmic wanderers, born in some of the most energetic processes in the universe. Our Sun is a prolific neutrino factory, producing a staggering number of these particles every second. In the Sun's core, nuclear fusion reactions generate electron neutrinos as a byproduct. These solar neutrinos stream out into space, with billions passing through every square inch of Earth's surface each second. But the Sun isn't the only star producing neutrinos. When massive stars reach the end of their lives and explode as supernovas, they release an enormous burst of neutrinos. In fact, about 99% of the energy from a supernova is carried away by neutrinos. Neutrinos are also produced in violent cosmic events like the collisions of neutron stars or the swirling of matter around black holes. Some of the highest energy neutrinos ever detected are thought to come from distant, highly energetic galaxies called blazars. Neutrinos are also produced right here on Earth. Nuclear reactors are significant sources of antineutrinos, the antimatter counterpart to neutrinos. Section 8. Neutrino Mysteries, Unanswered Questions in Particle Physics. Despite decades of research, neutrinos continue to puzzle scientists with a number of unanswered questions. One of the biggest mysteries is the exact mass of neutrinos. We know they have mass, but precisely how much is still unknown. This might seem like a trivial detail, but it's crucial for our understanding of particle physics and cosmology. Another intriguing question is whether neutrinos are their own antiparticles. Most particles have distinct antiparticles. For example, the positron is the antiparticle of the electron. But neutrinos might be special. If they are indeed their own antiparticles, a property called being Majorana particles, it could help explain why there's more matter than antimatter in the universe. The phenomenon of neutrino oscillation, where neutrinos change from one flavor to another as they travel, is also not fully understood. There's also the question of whether there are more than 3 types of neutrinos. Some experiments have hinted at the possibility of a 4th type, called a sterile neutrino, which would interact even less with matter than the known types. Section 9. The Future of Neutrino Research. What lies ahead? The field of neutrino physics is buzzing with excitement about future research possibilities. Scientists are planning and building even larger, more sensitive detectors to catch these elusive particles. One such project is the Deep Underground Neutrino Experiment DUNE, which will send a beam of neutrinos 1,300 kilometers through the Earth from Illinois to South Dakota. This experiment aims to unravel more mysteries about neutrino oscillations and potentially shed light on why the universe is made of matter rather than antimatter. Another exciting frontier is the study of ultra-high energy neutrinos from space. Projects like IceCube Gen 2, an expansion of the current IceCube detector in Antarctica, will search for neutrinos with energies far beyond what we can produce in particle accelerators on Earth. These cosmic neutrinos could act as messengers from some of the most extreme environments in the universe, potentially revealing new physics or pointing us towards the sources of cosmic rays. Neutrino astronomy is also an emerging field.